Hello, I would like to start by saying that I am very happy to present today the work that we carried out over the last few years in our group in Perugia. This is a work that was carried out in collaboration with the FACCTs company and with MPI COFO. And in this talk, I will walk you through the current state of energy decomposition schemes and wave function analysis tools in ORCA 6.1. And I'm happy to say that we have developed a wide range of new features, and we have worked very hard to bring them to completion. So I'm very excited today to be here and to have the opportunity to share the results of our efforts with you. So the first thing that we need to clarify, of course, for those who may not be familiar with the method, is what is the local energy decomposition, or LED? Now, LED is a method that provides a detailed analysis of interaction energies in arbitrary chemical systems based on high-level local correlation methods, such as the DLP-NO cluster approach. Now, the LED has been already successfully applied in several areas of chemical research. These include, for example, studying protein-ligand interactions, assessing the origin of the stability of molecular crystals, identifying selectivity determining interaction in transition states, and many other applications, some of which have been highlighted in this recent account. So I would like to start this talk by highlighting some of the key features of the local energy decomposition method as they are implemented in ORCA 6.1. First, LED can be used for bonding analysis in dimers. And in these systems, it can be used to break down interaction energy into electronic preparation, electrostatics, exchange, and dispersion, which essentially reveals how two molecules interact. So next, a very common application of LED is the study of host gas systems with many fragments. And in this context, LED allows an analysis of each fragment and fragment pairwise contribution. We also have a fragment pairwise LED scheme that we have recently published, which can be used to decompose the total energy exactly into pairwise interactions. We also support two-body LED and cooperativity analysis, which can be used to study non-additive effects. And I'm happy to say that starting from ORCA 6.1, we also have atomic decompositions available, which can be used to obtain atomic level contributions for dispersion and exchange, which I believe will open up many opportunities for molecular and material design. Finally, I also want to add that ORCA 6.1 includes, finally, a strategy for the chemically meaningful analysis of intramolecular interactions. That was a feature long requested by our user base. So despite the conceptual power of the LED method, I believe, it is important to recognize that the advanced features have traditionally required a complex setup, detailed analysis, and a deep understanding of the underlying theory. So this can be considered as the elephant in the room for LED, limiting broader adoption. So with the release of ORCA 6.1, we have taken important steps to address this challenge and make LED more accessible to users. So this is also one of the topics that I will be discussing today. So in particular, this presentation is divided into three parts. So first, I will introduce a set of tools designed precisely to make the local energy decomposition scheme more user-friendly and accessible. So essentially, our goal is to turn LED into a black box method. These tools are also being released today. Some of them are external and rely on Python interfaces. I will then present another recent advance in the LED scheme. That is what I just mentioned, so that for the first time, will allow a meaningful treatment of intramolecular interactions or covalent bonds. So in the second part of the talk, I will discuss new features developed in ORCA that allow the analysis of dispersion and exchange interactions with atomic resolution. And as I mentioned, these tools open up many possibilities for the design of molecules and materials. And finally, I will present the new implementation of the extended transition state method combined with the natural orbital for chemical valence, which is commonly known as ETS-NOCV method. I want to mention that this module has been completely rewritten in ORCA version 6.1 and now includes additional features and capabilities. And it is particularly well suited for analyzing the chemical bond between transition metals and a ligand. But as I will discuss, its applicability goes well beyond that. Before diving into the details, I would like to acknowledge the team behind this work. And in particular, I'm very grateful for the collaboration with the company FACCTs on making the LED scheme more accessible. And I'm also grateful for the collaboration with the MPI Field Fortune. And of course, I would like to thank the 3 members of my research group in Perugia who have focused on implementing the new features and capabilities that I'm going to discuss today. Okay, so now I will begin the first part of the talk, which is dedicated to turning the LED scheme into a black box tool. To achieve this goal, we realized that we needed tools to assist with both the setup of an LED calculation and the analysis and visualization of the results. To understand what is important, we can consider the interaction of a ligand with an enzyme as a case study. Now, applying the LED system, the LED method to this kind of host gas systems involves 3 main steps. So in the first step, we need to divide the enzyme and the ligand into chemical meaningful fragments. And this could be, for example, the functional groups on the ligand and the residues in the enzyme's active site. Now, for systems containing thousands of atoms, this step can be very tedious and time-consuming. So we need some tools that help us doing that in an automated fashion. Second, in the second step of the LED scheme, or the binding energy, which we can compute at the cathode cluster level, is decomposed into electronic preparation and interfragment interaction components. Now, collecting these terms from the ORCA output and visualizing them for a system with hundreds of fragments is again a very demanding task for the user. Finally, the interaction energy between fragments can be further decomposed into contributions, such as electrostatics, dispersion, exchange, which further increase the volume of data to collect and analyze. It is also important to mention that for systems with many fragments, the results from the local energy decomposition analysis are typically represented graphically using the so-called LED interaction maps. Here is an example of such a map showing the interaction between the ligand and the residues in the active site of the enzyme. And as you can see in this map, negative values indicate attractive interaction contributions, while positive values represent fragment polarizations or repulsive interactions. Clearly, having tools that allow a user to easily generate these maps is essential. So the first challenge I mentioned was fragmentation. And to address this challenge, an automated fragmentator was developed in ORCA 6.1. This tool can automatically partition a system, such as an enzyme, into chemically meaningful fragments, for example, as I mentioned before, the residues in the active site. So while this fragmentator has been implemented to facilitate multi-scale simulations, it can also be used as a straightforward way to generate meaningful fragments for the LED analysis. Also, in order to further support users in applying the more advanced features of the LED method, which I just examined a few slides ago, the FACCTs company has developed a series of tutorials and Jupyter notebooks that guide the users through each step of the process. For example, in the case of host-guest interactions, the notebook shown here assists the user with the entire workflow, from setting up the calculation to collecting the results, visualizing them, and interpreting the data. All these tools are being released today, and you can find here the relevant links for downloading them. Now, I believe that this marks a major step forward in making the LED method more accessible and user-friendly. And I would like to conclude this part by highlighting the excellent work of an historical collaborator of mine, Ahmed Altoun, who single-handedly developed a graphical user interface designed to assist users with the more advanced features of the LED method, from setup to visualization. In addition, Ahmed has written a comprehensive manual, which includes many of the practical tips and workarounds that we devised together when he was a postdoc in my group. So if you are interested in using LED in non-standard and customized ways, I highly recommend checking out his work. So now we move to the second part of the talk, where I'll present some new features added to the LED method starting from ORCA 6.1. And I will start with the covalent LED approach, or COVALED for short, for analyzing intramolecular interactions that was developed largely by Martina Colucci, a PhD student in my group at the University of Perugia. And I'm very excited about this development. So consider the interaction between two ethane molecules forming a dimer, where we define the four methyl groups as individual fragments. In the standard LED approach, the shared bonding orbitals between the fragments are assigned to one fragment in an heterolytic fashion, and this results clearly in charged fragments. This leads to unphysically large interaction energy between the methyl groups, which can be either strongly repulsive if the methyl groups have the same charge, or strongly attractive if they have opposite charges, as you can see here in the heat maps on the right. So while the overall binding energy in this case, that is the observable, is still accurate, the individual fragment interactions become chemically difficult to interpret, which limits the usefulness of the analysis. Now, starting from ORCA 6.1, it is now possible to instruct the LED program to treat specific bonds as covalent using a homolytic rather than heterolytic splitting. This is implemented through the COVALED approach. So as shown in the heat map on the right, this leads to a more physical and chemically meaningful description of the fragment interactions, yielding much smaller and more realistic interaction terms compared to those seen in the standard heterolytic case discussed in the previous slide. And the corresponding manuscript is currently in preparation. As an additional illustrative case study for the application of the COVALED approach, I show here the results of a fragment pairwise LED analysis for the interaction between two DNA strands forming human DNA, where the COVALED method was used to treat the bonds between the bases and the backbones. Now, the diagonal terms in the LED maps represent the base pair interactions, which are the strongest interactions in the system. And as expected, they are stronger for GC pairs than for AT pairs because, of course, GC pairs have one additional hydrogen bond. So you can see that thanks to the combined use of fragment pairwise LED and COVALED, now we have a way of estimating cleanly all the interactions operating in a complex chemical system, as I just demonstrated for the case of human DNA. The input for a COVALED calculation is straightforward. So essentially, in addition to the standard LED input, you only need to specify in the MDCI block which are the bonds that should be treated as covalent by listing the atoms involved. So in this example, two bonds are defined as covalent, the bond between atoms 0 and 1, and the bond between atoms 4 and 5. So this is very black box, and we are very happy with this development. Currently, I have to mention that this analysis is limited to closed-shell systems and single bonds only. So it does not support double bonds or cases where bonds cut through aromatic systems. But these are all developments that we have in plan for the future. The next new feature in ORCA 6.1 I would like to discuss is the atomic decomposition of the LED terms, specifically the London dispersion and the exchange interaction. This functionality was implemented by Gianluca Reni, a PhD student in our group in Perugia. In the atomic decomposition of the London dispersion energy, we have a breakdown of the dispersion, computing using LED, into atomic contributions. In my opinion, having atomic level resolution is potentially crucial in many areas of chemical research. For example, by simply summing up atomic contributions associated with a specific functional group in a transition state, we can quickly estimate how much that functional group stabilizes the transition state, which can be used, for example, to rationalize selectivity in a complex chemical reaction. In the figure here, atoms were colored based on how much they contribute to the total dispersion interaction energy between these two organic molecules, as estimated by the ADLD scheme. As you can see, only the atoms in close contacts contribute significantly to the interaction, which of course is something that is consistent with our chemical intuition. Importantly, ADLD is not limited to LED, but it can also be used in conjunction with DFT. So providing, in this case, a breakdown of the dispersion energy from dispersion corrections such as D2, D3, and D4. Additionally, it's also important that we can extend this approach to decompose the total correlation energy into atomic contributions. In ORCA 6.1, the atomic decomposition is also available for the interfragment exchange in the LED framework. And this exchange interaction is fundamental to the stability of many systems. So I believe that its detailed analysis could be particularly valuable for understanding, for example, the relative stabilization of different spin states, as it will be discussed in a paper that we are currently preparing. The input for ADLD and ADEX is very simple. Essentially, at the LED level, all that is needed to perform this analysis is a single additional keyword, for example, ADLD. And the same keyword can also be used in the DFT context to perform atomic level analysis of the dispersion energy. Finally, I would like to acknowledge the work of another student of mine who carried out most of this development during his master thesis in our group in Perugia, also in collaboration with the MPI Fukurin. This work resulted in the ORCA implementation of the full ETS-NOCV method, again, a long-awaited feature requested by many users. So what is the ETS-NOCV scheme? This method analyzes chemical bonding between two fragments within a mean field quantum chemical framework. So we have two fragments and we are restricted to a mean field approach. And so it is a method that is less general than the LED scheme, but it provides useful and complementary insights which are particularly valuable for understanding and studying metal ligand bonds. So this method consists of two components. First, the ETS part decomposes the interaction energy between two fragments into polyrepulsion, electrostatics, orbital relaxation, and dispersion contributions. Then the dispersion term in the ORCA implementation can, of course, be further analyzed using ADLD, as discussed before, into atomic contributions. Second, we have the NOCV component of the tool, which breaks down the orbital relaxation term into contributions corresponding, for example, to sigma pi interactions, which help clarify the nature of the bond, again, between a transition metal and its ligand. Here are the key features of the ETS-NOCV implementation in ORCA. And these include a complete implementation of all terms in the ETS-NOCV method. Also, our implementation is fully automated. So there is no longer need for prior individual fragmented duct energy calculations, but you can generate the entire output from a single input. We have support for both open and closed shell systems. And this scheme is available for all mean field approaches, so DFT and R3FOC. A unique, I guess, feature of the ORCA implementation is the support for double hybrid functionals and for 3C schemes. Also, now with using ORCA plot, it is possible to visualize the NOCV's deformation densities in a simple way. And I also want to mention that our implementation is fully parallelized. Finally, as I mentioned before, the dispersion term obtained with the ETS-NOCV method can be decomposed into atomic contributions using the ADLD framework. And with that, I would like to thank you all for your kind attention, and also our friends at FACCTs and COVALED for the great collaboration. And of course, I would like to thank my group at UniPG for the amazing work we have been doing together.